What is a multiplexer? This is a multiplexer, and this is a machine that uses multiplexers. In this video, I'm going to go over how a multiplexer works as a logical component, and then later I'll show you an example of a machine I've made using several multiplexers to perform a more complicated task. For this video, we are going to look at multiplexers with 3 inputs and 1 output, just to keep things simple. However, you can also have multiplexers with more than 3 inputs, but we're not going to worry about that today. So, a multiplexer is a type of logic gate which, as I said previously, takes in 3 inputs. Let's call these inputs A, B, and cell, where cell is short for selector. As you can see from this diagram, input A has a small 0 next to it, and input B has a small 1 next to it. The output of this logic device, let's call that Y, is going to be either A or B. The way you determine whether it's going to be A or B is based on the input of cell. If the value of cell is 0, the output from the multiplexer would be the value A, since A has a small 0 next to it. Likewise, if the value of cell is 1, the output from the multiplexer would be B, since it has a small 1 next to it. Here are the truth tables showing this logic. In this truth table, the values being passed around are 1s and 0s. However, you can also see that there are some x's in the table. This means the value does not matter. Let me walk you through it. As we said before, if we set cell to 0, the output of Y will equal the input of A. This has been highlighted in yellow. As long as cell equals 0, if A is 1, then Y will also be 1, and if A is 0, then Y will also have to be 0. In this interaction, the value of B has no effect whatsoever on the output. This is why we've put the x's there. Simply, we don't care for the x's. The same logic is applied when cell is equal to 1, but in this case, the output of Y will always equal to the input of B. The values of A do not matter. Now, let's have some fun and apply this logic. For reference, I put in brackets in my script here to be very sarcastic. This is Bob. We don't like Bob. In fact, we don't like Bob so much that we are building a machine using our newfound multiplexer knowledge in order to, how do I put this lightly? In order to end Bob's life. This machine is built using some key components. We have 4 inputs of the machine, them being the switch, sensor 1, sensor 2, and the button. The switch allows the machine to go between 2 modes, manual and automatic. In manual mode, the button directly causes the servo to go down. When the button is pushed, Bob gets squashed. That's how it is. In automatic mode, the button won't do anything, and the servo going down is entirely dependent on the sensors being triggered. Now onto the outputs of the machine. The outputs of the machine are the servo and the LED. The servo is the machine which squashes the bug. The LED is the one next to the switch, which lights up based on which mode the switch is in. When we're in manual mode, the LED is turned on, and when the LED is turned off, we are in automatic. Okay, now onto what the machine actually does. First, manual mode. We want the mechanism to work so that if the button is pushed, the LED will turn on and the servo will go down. Simple. However, automatic mode is where the real fun begins. In automatic mode, the button will no longer work. Instead, the servo goes down depending on the 2 sensors. If neither sensor detects anything, nothing will happen. If one of the 2 sensors are triggered, then the servo will go down and squash the bug. We can call this a small bug, since it only triggers one of the sensors. However, when both sensors are triggered, like shown in this diagram, the servo will begin to oscillate and it will destroy every last fiver of Bob. Naturally. Now, time to implement the logic. Here is the logic. It is a lot, so let's walk through it step by step. Here on the left, we have the inputs: fire, sensor 1, sensor 2, the oscillator, and the mode. Fire is the button, and mode is determined by the switch. You may notice that NOT gates are placed immediately after the inputs. These basically ensure that the sensors are working the right way around. We want the sensors to output a value of 1, indicating that something is true, if there is an item in front of it. First, we have the circuit which determines whether the bug is large or small. As we discussed, this is determined by the number of sensors active. Therefore, as you can see in the implementation, a small signal is outputted by making use of an OR gate, and a large signal is outputted by making use of an AND gate. The next steps involve multiplexers and can get a bit more complicated. Multiplexer 2B, shown highlighted in this diagram, is used to tell the output to squash the bug once, if a sensor is triggered. Input A of the multiplexer is ground, labelled as GND. This is a static input of 0. Input B of the multiplexer is voltage at the common collector, labelled as VCC. Essentially, to put it in simple terms, this is another static input, but in this case, the static input is 1. The value is always going to be 1 going into here. The output of the OR gate, which was used to determine if the bug is small or not, is used as the cell input. By doing this, if no bug is present, the cell will be 0, and the output of the multiplexer will equal to A, which, as we said, is always going to be 0. On the other hand, if any sensor is detected, then cell will have a value of 1, and the output of the multiplexer will equal to B, which is always going to be 1. To simplify, if something is present, the machine will squat the bug and hold it down. Otherwise, it will just stay up. However, looking back at what we want the logic to actually do, we want to make it repeatedly swat the bug if both sensors are triggered. At the moment, it will only just hold it down. Therefore, we're going to add another multiplexer to check if the bug is large. Going back to earlier, we created an AND gate with both sensors. We can take this input and connect it to the new multiplexer, multiplexer 2C. The goal of multiplexer 2C is to check if we need to swat the bug once, or repeatedly swat the bug. Input A of the multiplexer will be the output of a previous multiplexer 2B, which determines if it needs to be swatted. Input B of the multiplexer will be the input OSC, oscillator, which tells the machine to repeatedly oscillate, and aka just swat the bug multiple times. In total, the multiplexer will know to swat the bug repeatedly if both sensors are active, thanks to the AND gate being used as the cell input, and it will know to otherwise swat the bug or not swat the bug, depending on if one or none of the sensors are active. Now, the combination of multiplexers 2B and 2C are working together to know how and when to swat the bug. On top of this, we want to add a multiplexer to determine which mode the program is in. The logic we just created works for the automatic mode, where it actively checks if the bug is present and what to do correspondingly. We want to implement logic that allows the user to switch the mode of the program between this and a manual mode, where the user can push the fire button to swat the bug as they choose. We will use the multiplexer 2D to do this. We can use the input of the switch to toggle between these two modes. This will be the cell input of the multiplexer 2D. The input A of the multiplexer is connected to the fire button. If the fire button is pushed, the swatter will go down. If it's not pushed, it stays up. On the other hand, the input B of the multiplexer is connected to the output of multiplexer 2C, which controls the automatic output. Last but not least, we have the multiplexer 2A. This is the simplest multiplexer, as its job is to control the LED light. The light switches on depending on what mode the machine is in. We connect GND, which gives the static value of 0, and VCC, which gives the static value of 1, in order to turn the light on and off depending on the mode. Once again, mode is the cell input of the multiplexer, as it determines if the light should be on or off. Okay, finally we have two outputs, them being the servo and the LED. When the servo has an input of 1, the squatter goes down and it squashes the bug. When the LED gets an output of 1, it turns on, otherwise it turns off. Pretty simple. Now, what you've all been waiting for, the implementation of the machine. Now that we've gone over how each multiplexer works, I can show you the machine working in practice. Here is my past self from a few months ago showing you the machine in all of its glory. I forgot to commentate on the videos back then, so here I am now trying to remember what I said. Enjoy! As you can see here, I've connected the machine to my computer, and the computer is running a virtual machine, Xilinx, in order to run the logic that I was showing you earlier. Here we have manual mode, indicated by the light being turned on. Thank you past me for pointing. Thanks. Now, if I push the button, the servo goes down. I know, it's really magical. As you can see here, I've put Bob on the machine. Both sensors are being triggered, but since we're in manual mode, only the button can affect the servo. Now, automatic mode. We flip the switch and the LED turns off. As you can see, the button does nothing. The servo is dependent on the sensors being active. When I put Bob on the machine and only one sensor is detecting Bob, the servo goes down. However, if both sensors are detecting Bob at the same time, the machine will oscillate and, well, it oscillates and destroys the large bug. Thank you for watching. Make sure to like, subscribe, share this video to as many people and friends, family, everyone you know. Just send this video